Hi, let's see if we can start and develop, a tutorial on the design of a one-bit adder using structural equations. For example, the plan A, right? An idea that is going to be the entity that is represented here. You have 3 inputs, and then you generate 2 outputs. You can input the AI, the BI, the 2 operands, along with the carry input. And so the circuit will generate 2 outputs, the sum and the carry out. So in some way, this is a full adder that can go concatenated, and you can go rippling the carries from one chip to the next. So this is going to be the idea, designing this full one-bit adder. And so we have to synthesize the circuit in a given chip. For example, let it be a Cyclone 4 from Intel, right? So the objective, you have to have an objective all the time. The objective is this kind of sentence, for example. Invent a combinational circuit that works a one-bit full adder through table, using the VHDL design flow sequence. And in this case, we will choose the electronic design automation tools, the Quartus Prime Lite, plus the Model Sim Intel FPGA Starter Edition that goes together for free. And to start, everything is related to the VHDL design flow. We have to go through the 4 basic steps: the specification, planning, developing, and functional simulation. That is what we call the basic design flow, because what goes next, and we will consider it from P4 and on, is going to be the gate level simulation and timing analyzer testing, which is going to be something that is going to be related to the technology. So in the end, you can continue the design flow down to the chip programming and laboratory prototyping. So that's the full process. And you've got that thing in digsys with more steps and subdivisions, but in the end is this kind of sequence that you have to have in mind. So the specifications go fast. First of all, absolutely, we have to go understanding everything related to the symbol, the truth table, the timing diagram, an example of combinational circuit that is in the marketplace, something commercial. For example, then you must know, for example, how to add together, how to build a larger circuit of the same kind using this kind of chips, things like that, because those ones, like the other one-bit, are basic blocks that they can go together to build larger circuits. So the specifications consist on all these devices and resources that goes together to fully understand what is going on in a project, because in the end, a project is something real, a chip that has to do some kind of function. So the first thing that goes here, that now you are beginning with this, and is to have this clear in mind. Understand the specifications. All right. And for understanding the specifications of every single project that we've had here in this subject, you know that we have digsys. It's a kind of an electronic book that allows you to browse many examples and ideas. For example, this time, if you are pretending in the invention of an arithmetic circuit, probably you have to focus in P3. Here is where you are going to find this, right? In a way that this video recording is nothing but an extension of the examples that are already here in this web. So we are going to go and just go and for a full use of this web, right? So for example, if you click P3, it's centered on radix 2 devices, arithmetic circuits, circuits that are going to work with basic binary numbers, comparators, adders, multipliers, and the like. The unit is centered in something larger, for example, an 8-bit adder. All right, like if you go and and connect together two 74s ACT 283 chips. So the unit has two aims, talking about arithmetic circuits, the different ones that you can see, and then talking about as well the plan C2. All right? But what we've got in mind now is not the 8-bit binary adder, but something simpler. So that something simpler has to be an example in the learning material that you see here in this basic unit on arithmetics. So the basic material has to have something like a 1-bit adder, and here you are, all right? Here you are, a full tutorial on the 1-bit adder. So if you click this link, you will see in green, you know, because it's a tutorial, it's fully designed and is here, so you can take advantage of and having everything from the very first truth table to the last test bench, stimulus, you know, everything is here. So, and probably it is solved in several ways. Okay, so for example, here you are the tutorial, which consists of plan A, plan B, and even plan C2. So this is inventing the 1-bit full adder using several plans. But, you know, let's talk about the specifications briefly, because, you know, this is not the time for explaining every detail of the table. That goes aside, that goes apart. You better take some sheets of paper and try to understand what the circuit is doing for fully understand, you know. The idea here is, you know, if you have 0 plus 1 plus 0, you will have a 0 in the carry out and a 1 in the sum. If you have a 1 in the AI, a 1 in the BI, and a 1 in the CI, you will have, you know, this is 3 ones, so you will get a 3, but the 3 in this chip is a 1 in the sum output and a 1 in the carry output. So this is the way it works. So this is nothing but a conventional truth table. And so below you can see the next picture, which is the same truth table, but in some way in time. And here you will consider the minimum duration. And when you are here, you better continue the explanation, making some annotations. For example, okay, for example, you may take one of these inputs. For example, if you've got 0 in the input A and 0 in the input B, right? But 1 in the carry input for a while, for example, this time, the inputs are going to be freezed to this value, 0, 0, 1. This is nothing but one of the combination of the two tables, the one which give you an output, 0 in the carry out and a 1 in the sum, right? So you see, the way that you've been sketching this, you see that this is kind of a minimum pulse here, because something like this is larger. So this time, for example, here, when you are applying in time 0, 1, 0, that precisely is going to generate the same output, 0 in the carry and 1 in the sum. In this time here, you see, is larger than the other one. So if this one here can be taken as a constant mean pulse, the other one may be perfectly well a multiple of the mean pulse. For example, 1.7 times the mean pulse constant, right? And so on. So you can go and refer all the times in this diagram to this constant. So easily later it can be represented, you know, in nanoseconds or microseconds or milliseconds, whatever time unit that is convenient for you, okay? So it is going to be good to represent the duration of the stimulus, you know, for example, this time here, as a multiple of this mean pulse constant. For example, here, if this is mean pulse, you may say that this is roughly 3 times the mean pulse. So, you know, it's everything like that. It's all the time the same way. And, you know, this is, if you may imagine the circuit now, this is nothing but the algorithm. Okay? This is the algorithm. the system goes and adds 1 plus 1 plus 1, and in this way generates a 1 in the sum and a 1 in the carry, for example, this time here when you are applying these signals, okay? So this is the generic algorithm, and this is just a simple example. All right. So in this way, you can go studying this as much as necessary. Don't rush and take it easy, and because those are going to be your first circuits, spend as much time as necessary here talking about the specifications, because this is what the circuit has to do in the end. All right. So the next step is the engineer point of view. You are going to invent the circuit, and in this way, if you talk about planning, you have to have many resources and many ways, or some ways to do it, because it is not a single way to invent a circuit. You can invent it in 1,000 different ways. So for example here, what we are studying here in this circuit and systems, in digital circuit and systems, CSD, is something like this, you see? We are proposing you to study the circuits using 3 different plans, okay? 3 different plans. And conceptually speaking, they are going to be different. So, for example, the plan A is going to be based on an structure, gates of any kind, gates, NORs or ANDs, whatever, but, equations. The plan B is going to be different. What are you going to pretend in the plan B is to try to copy the truth table, directly to VHDL, because, the plans are going to be for VHDL, right? So the plan B is going to be behavioral, because we'll try to copy the truth table directly as a text file in VHDL. And the plan C2 is different because it will consist of in using blocks, all right? The smaller components or components of other kind, so that in the end, mixing components and signals, you'll be able to invent the circuit you like, all right? So the point here is that every plan has, it is going to generate a different project. That's the key point here, right? So if you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 plans, indeed, you may very well think about 12 different VHDL files describing at least the way the one bit adder is going to work. So this time we will focus our attention in the one that is in orange. You will take any kind of equation to describe the functionality of the one bit adder truth table. All right. So planning, the picture that you've seen, the slide, is what you see in CSD. Exactly that idea of plan A, multiple possibilities, different equations, plan B, and plan C2. All right, so here you can invest time studying the different possibilities, and for example, we can just generate, class nodes. For example, if I click here, the implementation, all right, what I see is the discussion of the table and the entity to design by means of equations. So you see, this time the CO, for example, has been organized as a sum of minterms, but no one is preventing you or is forbidding you to go and operate the operations. You can just organize the equations in another way following some Boole algebra rules. For example, here you can have a common factor, AI and BI, so CI not and CI go in a bracket, but you know that CI not plus CI is all the time 1. So in this way, you can have something simpler, which is a product. So from these two minterms, you get a single product, AI, BI. And the same here. If you are having a common factor, CI, what you see here is nothing but a shore. So you've got C0, the carry out, as the carry in propagated in some way by this term, which is a shore of the operands AI and BI. And then you see the carry 0, it's the same generated by this other term, which is a AND. So if you see the equation like this, and if you go the same way with the zoom out, you can realize that the zoom out is nothing but a shore of 3 inputs. So from the equations, you get a circuit, all right? And you may imagine that this circuit very well can be translated to VHDL using the architecture based on equations, okay? So this is what we have in mind. So when the equation has been selected, the only thing now is to go and develop the project. For example, using the EDA tools from Intel, right? So this is the next step. And this time it involves, you know, a computer, it involves project location and everything. So this is what we are going to do now. Try to develop the circuit, which means getting a circuit and being able to visualize it, for example, by means of the RTL view, which is some kind of ideal schematic, right? And because it's a tutorial, you know, the file that we require here, which is the translation of the plan, is already in the digsys web down there. After the plan, after having got a plan, you can translate that plan into a file. So, and this is, for example, an example of project location, right? So in the end, we expect from the Quartus Prime a kind of a circuit like this, the one represented here in the picture 3. So let's go and save the file as, you know, save the link of the file as something that has to be solved in a given folder. For example, you can name it other 1 bit A7, because this is the way, the equation that you are going to use. So save the file. And now, because, you know, it's a very simple project, only one file, you can start the project, just a new project in Quartus, right? So, but it's a good idea as well to keep an eye on the file, okay? To be sure that this is the perfect translation of our plan. For example, you know, you've got a library, and then you have the entity definitions, which has to be a perfect match with the picture, the symbol, and then you have the architecture, and the architecture is nothing but the logic equations, 2 of them. Here you are, the one which is based on a shore, and this is the one that we have got there from the one which was a sum of products, or the one which was a sum of minterms. So this is the equation that is going to represent the carry out. And that's all. Very simple, right? Just a translation of the 2 equations. So when you've got that, you can switch off the editor window. And now is your turn to go and launch the Quartus Prime. So this is the Quartus Prime Project Navigator on the platform. So let's go and say new project wizard, and next the project location, the working directory, is going to be the one that we have decided in L, CSD, and now P3, and it's going to be the other 1 bit A7. So let's select this folder. The name of the project is other 1 bit, but as all the projects, we will name them _PRJ, referring to the project idea. But the top entity is other 1 bit. That's the name of the entity to be synthesized. So you say you click next, an empty project. Now you because you are in the right folder already, you click here, add files, and the 1-bit adder has been now selected and added to the project environment. So it's a VHDL file, has been correctly identified. So you say next. Now you are going to select a cyclone free, and for example, it's going to be filtered to be the 115 F29C7, okay? The one which is, you know, in the lab, because for example, in the lab, we've got some chips, some FPGA chips, okay? So you can type digsys, and typing this, you can see very well that in electronic devices and companies, if you click Altera or Intel, you see, for example, that this board, which is available, all the boards are available in the lab. So for example, this is a complex PLD, the MAX, and then this is a Cyclone 4. A Cyclone 4 EP4CE 115F29C7. This is the one that it's populating this board. So this is the one that we are going to use in this tutorial. Okay, so that is going to be our target chip. So you say next, and now you have to select the tool, which is Model Sim Altera, and the language is VHDL. Okay, next. So you have a final summary of everything you've been typing. So you say finish. And now the machine recollects what is in the VHDL file, and has understood that there is a top entity named other 1-bit. So now is your turn to go and compile. Start a compilation, which is going to launch the synthesis of the chip. You see, it's a long flow that goes through analysis and synthesis, and then you have a feeder, and then there is an assembler and other tools associated to the gate level simulation and things like that. But basically, it's all about analysis and synthesis and feeder and assembler, until the end you have your technology view associated with the chip that you are designing. So after a couple of minutes, you have the compilation finished. So now it's time to see, you know, the way this entity, this VHDL file, has been translated into the circuit that is represented by this pair of equations. So this can be inspected in Tool and Netlist Viewers and RTL. So the RTL is going to show you the circuit, which is pretty much what you had in mind. You see a short of 3 inputs and then some gates to fulfill with a carry out equation. Okay, and you see perhaps it is slightly different from the one that you have organized or not, but more or less it is what you have stated in the equations. Okay, so now is your turn to take this picture and add the picture annotated in the report, you know. So this can be solved, for example, using any kind of tools like snipping tools. The snipping tool can be used to take a picture of this with some room to have comments. So now with your pen, you know, and the paper, after printing this thing, you can go and say, right, so this is the SO. So okay, because SO, I see that is carry I, shore, AI, shore, BI. So that's what been expecting. The same with a carry 0, right? So you have to go and interpret a little bit the circuit that has been generated. So now you can continue inspecting. Instead of the RTL, you can inspect as well the other one, which is here accompanying the RTL, which is the technology map. So you see exactly for this specific chip how it has been generated. Well, you see a couple of logic cells that are going to develop an equation each. One logic cell will develop the sum out, and another logic cell the equations, you see, related to the carry out. And then you've got buffers to connect the internal signals of the FPGA to the ports. Okay, so that's the circuit that has finally synthesized in silicon, you know, in the lattice structure of lookup tables, because if it's going to be an FPGA in the end, the logic cells are based on lookup tables. So that's the technology view, right? So now it's time to annotate it in some way or another. You can say that here you've got two cells, which is okay because you have two equations, so it may be right. So what goes next now is continue the processing and starting the tools for going to the final step, which is the functional simulation. So, you know, once you've got the circuit, you have to continue to the end, which is functional simulation. So the functional simulation is based on the idea of test benching. You have to connect the component now, the component that is going to be the unit or device or chip under test, inside this new entity that you are going to call test bench. You see, a closed entity with no ports, so everything is inside. And what is this everything? Well, the unit and the test in the center, and then you have some signals, wires and cables to connect, for example, the outputs to a waveform viewer, a diagram which is going to show you something like the timing diagram, and then from the input side you have the possibility to connect every input to a process that will stimulate the circuit. Okay, that's the idea. And because we are talking about very simple circuits, combinational circuits, we are going to simply use a one process, you know, we want to call it stimulus process or something like this, all right? But the test bench itself is going to be generated automatically by the Quartus Prime tool, right? In which way? Well, so you have to go to processing and start precisely the test bench template writer. So you click down here and the machine starts working in something that is going to be the diagram, the schema that you've seen before in the slide. So you see it is placed in simulation model sim and has a name, other 1-bit VHT. VH because it's VHDL transcription, but T because they mean test benching. But we will copy the file to the folder, to the root folder where we have the project, and we will rename it as we do all the time. So it's going to be something automated like this, going to the folder simulation model sim, and let's copy the other 1-bit VHT, two folders above, because here is the project folder, paste it, and now let's rename it conveniently 1-bit TV, and now VHD. Let's change the file extension because in the end it's nothing but a VHDL file, so let it be like this. Okay, so this is going to be the skeleton of the test bench. It is empty, you know, there's nothing inside. You see, it is generated automatically, but you know, you have two empty processes here. So how are we going to learn how to input stimulus for the signals here? Well, from the web. Okay, so let's go back to the web, to the tutorial that we have in mind, and the tutorial that was in P3, the 1-bit adder, and you can browse 1, 2, the planning, the development. It is here. You see, we've got the circuit very well like this. So now it's time for testing. So when you are in testing, the testing section is going to generate, in the end, results like this timing diagram that you see here. You see the truth table in time. But you have an example of test bench here. So that's the point. You can go here and copy the stimulus, right? But if you like, first of all, let's start the process, the simulation process in Model Sim. So we go back to Quartus, and from Quartus itself, we can launch the tool, which is going to be run a simulation tool, precisely the RTL simulation. So that's the time for starting a new project, but this time is going to be a simulation project. So the computer, in the end, is going to launch, you see, a new window, and once settled, you will go and click File, New, Project, right? And we will use once and again the same naming conventions to make it easy and as well easy to remember. So let's go for the folder location. It's going to be CSD, and the other one bit A7. That's the project location. You say OK. The project name, is the name of the entity to be designed, underscore, this time functional simulation, right? Functional sim, that way. And then the library where the entity and all the structure of the entity design is going to be saved is going to be called work functional. So you do that all the time, changing the name of the chip that you have in mind. Whatever it is, a decoder, it's going to be decoder 3 to 8 functional sim. All right. So you click OK. And now it's time for adding files to this project. Which files? Well, the only one consisting of the architecture, the 1-bit adder, and the 1-bit adder test bench. So you can take both and save them into this project and close this window. So now it's time to see if the machine has a good interpretation of what we have in mind. So you click now Compile All, selecting the window, and the compilation is successful. So now it's time, before launching the simulation, that the test bench is empty. So now it's time for, comparing this one that is a simple skeleton with the one in the web, which is finished. So for example, you see that before the begin, after the component, in this one from the web, you have a constant, the min pulse, that was in the skeleton, that was in the sketch of the timing diagram. So you copy the min pulse to the file in the right place. You see it is colored correctly, it is understood correctly. So min pulse for you is going to be, for example, 12 microseconds. So you can run the simulation for example, 300 microseconds. That's enough time for simulating several stimulus, right? Which stimulus? Well, the ones that you are going to annotate here as a process for the input. So you can suppress, you can delete the empty processes that you've got here and make room for copying now from the web file, not the instantiation of the chip, because this is something automated, but what is handmade, the test bench TV process, that one. So you can copy it all and paste it the same way, so it's going to be colored correctly. So this is the process, where you are inputting signals. For example, here you are, 000, 001, and wait for a while, 001, 010, 011. It looks like that this time. What are you doing here? Is inputting all the truth table values, the 8 of them. So from 000 to 111, which is okay, because in the end you will have the possibility to check the full table of the 1-bit adder. So once this thing has been solved and amended, you switch off the file and go back to your Model Sim project. And you know, because you've made modifications, the program, you know, the model sim has noticed this. So now it's time to recompile it to see that you've not some kind of error in the listing or anything, the syntax, everything is okay right now. So now it's time to simulate and get results. So now you can start the simulation, right? Which simulation? Well, work functional, you see, and precisely the other 1-bit VHD TST, because this is the name given by this Quartus Prime skeleton to the test bench that has no inputs or outputs, this box that represents the fixture for testing. Okay, I'm referring to this fixture here in the slide. You see, the box that is the entity test bench this time has this name. All right, and the name that you've got here in Quartus. Okay, so the name is the other 1-bit VHD TST. So that's the entity. So you say okay, and now the machine starts the processing of the simulation. So all the inputs and outputs are identified here. You have the top entity, other 1-bit. So now with a right click, you select this top entity, and you may say something like add to wave what? All the items in region. If you do that, you get all the signals in position and in place. So now is your turn to do something like, for example, separating. That's a good idea. Let's separate and organize the signals as they were in the table. So you can add, you know, a divider, for example, outputs. That way, outputs. So carry and zoom, and then AI, BI, and CI. That's the thing. So now you can go and say run, okay, for example, 400 microseconds to see if everything is okay. So now you can select the window after simulation, and you can go here and say zoom all. So you see, at the beginning, the signals were undetermined, but there is a point where every signal gets a value, and so you start with 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, you see. So it looks like that the circuit works as expected. So now it's time again for what? For using the snipping tool, for example, which is a very simple idea, and generate a new picture like this. All right, and here again you can go annotating results. This is a kind of customization of the two tables. So for example, you can tell that here you are inputting 0, 0, 0, and you get 0, 0. So this is okay, and this is up to this point, right? Later, all this time, you have a different input, which is 1, 0, and 0, you know. So the output is 0 in the carry and 1 in the zoom. So it looks like the circuit works, right? So this is in some way the end of the steps, the designer steps 1, 2, 3, and functional testing, because you know this project can be continued when you like it, considering a gate level simulation. But let's wait for the next chapter in order not to do all at the same time. So now is your turn to repeat this tutorial as many times you like, considering different plans, because now the objective here is not to work that much in another, but to work with the tools and see the sequence of operations that you can go through in order to get results. And you know, this idea and this capacity that you have once you get results from the computer to analyze them. For example, again, this is a 0 between this time, you know, and this timeline, in this period of time, you are inputting a 0 in AI, okay? You are inputting a 0 in BI, and then a 1 in the carry in. So what are you doing here is AI plus BI, you write, and then plus the carry in from, you may say, the previous section of another other. So you get the sum 0 and the carry out. So this is it. You carry I is 1, AI happens to be 0, and BI happens to be 0. So what you get is a 1 and a 0 in the carry. This kind of analysis is the one that I'm referring to, okay? So yes, you've got a 0 in the carry and a 1 in the sum. All right. So this kind of picture, discussed and examined and reviewed, when it works, is the one that you need to add like that in the report. All right. So that has been the full idea of an example of 1, 2, 3, 4 steps that, you know, we are not going to move never from this position. 1, 2, 3, 4. In this way, you will see the systematics of what is called engineering, you know, something repeatable and reliable in the end. Because if all the circuits are going to be similar, with the same kind of tools, with the same proceedings, and the same mechanisms, so in the end, you will have this kind of, you will get all the necessary ideas to go advancing towards more complex circuits, right? So that's all. Thank you.